Good morning, everyone, and well done to those of you who are keeping up and just plugging away. We know it's difficult being away from school, keeping up with the work, but we are well aware that many of you are, and well done. Normally around this time of year, we'd be preparing for our end of year assessment, and there are often some difficult decisions to be made in the light of that. People that are perhaps not getting enough marks to sort of continue on to year 13. Now, obviously, we haven't got that opportunity, but what will be happening in September is we will be having early mock exams in September, and particularly in maths, we are going to be writing an assessment based solely on the material covered by both Mr. Godber and myself during this period of closure. So it'll be his pure maths and my statistics. I'm not telling you that to try and create stress. I promise you it will be a very straightforward assessment, no nasty trick questions. And I absolutely promise you that if you are someone who has worked through both mine and Mr. Godber's videos and done all the practice, you will score very close to full marks on that assessment. We're not trying to trip people up. We just want to make sure that people understand the material that's being covered, because we can't afford to give up some of year 13 to recapping year 12, no matter how much we would like to. So keep at it, keep plugging away, and keep in touch with us whenever you have problems. And let's do some sums. Today we're going to talk about tree diagrams. Okay, so here is a question from last week. We were talking last week about mutually exclusive and independent events. Mutually exclusive events are easy to spot on a Venn diagram because they are events that can't both happen at the same time, so there's no overlap. So these two events, A and B, are not mutually exclusive because they have an overlap. Independent events are harder to spot. This is where one event affects the other. But we can test for independence using this rule here, and that was what we were doing last week. So in this Venn diagram, if I add up the probabilities I know, I get 0.75. So I know that x is 0.25. And that means the probability of A, that's all of the probabilities in the A circle, that's 0.65, the 0.4 and the 0.25 added together. And the probability of B is 0.3 and 0.25, so that's 0.55. And the probability of A and B, which when we're talking about Venn diagrams, we use that notation. Remember, that and that mean the same thing, is the overlap, 0.25. So we just need to ask, if these events are independent, probability of A multiplied by the probability of B will equal 0.25. So 0.65 times 0.55, if the events are independent, will equal 0.25. Now, surprise, surprise, it does not. So from that we know that A and B are not independent. They're not independent. So what is the opposite of being independent? Well, the opposite of independent is referred to as conditional events. So if two events are not independent, we say they are conditional. One is conditional upon the other. And in that case, the probability of them both happening is the probability of one multiplied by the probability of the other, given that the first has happened. So we say that the probability of A and B is the probability of A multiplied by the probability of B, given that A has happened. And that word given is sort of a loaded word. It crops up a lot, particularly when we come back to this in year 2. Now, I'm not a huge fan of formulas like this because I think this is common sense. So let's do a question which you would have done at GCSE, which is a conditional probability question. So here we've got a question about Charlie. Now, Charlie has two ways of getting to school. He can take the bus or he can walk. The probability he takes the bus to school is 0.4. So I know straight away what the probability that he walks is. Easy peasy. The probability that he's late to school if he takes the bus is 0.2. So he might be late or he might be on time. So I'm going to put OT for on time. So the probability that he's late if he takes the bus is 0.2. So I know the probability that he's on time if he takes the bus is 0.8. The probability that he's late to school if he walks is 0.3. So if he walks, and he's got a probability of being late of 0.3, so that's 0.7 that he is on time. So what we've got here is the probability that he takes the bus and he's late, sorry, this is a land sign, not an E, is the probability that he takes the bus, the probability of B, multiplied by the probability of L given B. So that's multiplied by the probability that he's late given that he's taken the bus. So this is the probability of B, and this is the probability of L given B. So that's just what that notation means. And the reason I'm not a fan of it is because I think this is common sense. I think if I'd given you this question, you would have got full marks without having worried about that at all. So that's one way that he can be late to school. So that's 0.08. The other way he can be late to school is this. So that's the probability that he walks and he's late. So that's 0.6 times 0.3. So that's 0.18. So the probability that he's late, that's this or this, we add those together. So the probability that he's late, those two added together, 0.2. I have to be careful here, so I'd have to put a little correction in my video. Oh, sorry, you can't see that. There we go, 0.26. These events are mutually exclusive. They can't both happen. So the probability of one or the other, we add them together. That was from last week. But again, that's common sense, isn't it? Now, I'm going to be a bit controversial here. I think that rarely at A-level do we need to draw a tree diagram. I think often questions which could be answered with tree diagrams don't need tree diagrams to solve them. Now, I disagree here with my esteemed retired colleague, Mr. Mawson, who would draw a tree diagram for everything. But here's a question where I hope you can see why I wouldn't bother drawing a tree diagram. And to try and demonstrate why I wouldn't, I'm going to draw one. Okay, so a bag contains 13 tokens and they're blue, red and yellow, and 2 tokens are taken without replacements. That's key, isn't it? Because that means that once you've taken your first one out, so your first one could be blue, red or yellow, and this probability is 4 out of 13, for example. When you take your second one out, which could still be blue, red or yellow, there's only 12 left. So if the first one you take out is blue, you've only got 3 blue left, and that's out of a total of 12. And that would be repeated here, blue, red, yellow, blue, red, yellow. So can you see why I'm already thinking, I don't really want to draw a tree diagram here. It's just too fiddly, and it's very hard not to make your branches clash, and I'm going to have probabilities all over the place. If the question says draw a tree diagram, yes, I've got to, but it doesn't, does it? It says find the probability that both tokens are yellow. Well, the probability that both tokens are yellow are the probability the first one is yellow multiplied by the probability that the second one is yellow, given that the first one is yellow. So what they're asking me for is that outcome there. I think I can do that. I don't think I need to draw the tree diagram. It might help me visualize it, but I think I can do that without bothering to draw the tree diagram. A third token is drawn from the bag. Are you kidding me? So I've got to do 3 branches off each of these? Well, I'm not sure. You do need to. All it asks is write down the probability that the third token is yellow, given that the first 2 are yellow. Okay, so if I just think about that probability down there, sorry, I have to move that probability down there. Well, the probability of the first one is yellow. Can't see how many there were. 6 were coloured yellow. So that was 6 out of 13. So the probability of the second one would be yellow. Well, if our first one was yellow, there'd be only 5 out of 12. So all they're asking for here in part B, not the probability of 3 yellows, it's not asking that. Part B just wants to know what's the probability there, that the third one is yellow, given that the first 2 are yellow. So they're saying, right, we're here, what's the probability of that branch there? Question C, the probability that all 3 tokens are different colours. Well, I'm going to end up with 27 branches, aren't I? 27 branches. But find the probability that all 3 tokens are different colours. There's only a limited number of ways that that could happen. So I'm wondering if I can answer that one without a tree diagram. For example, blue, I'll do it here, blue, red, yellow. The probability that the first one is blue, well, I'm going to have to go back up here, is 4 out of 13. If the first one is blue, I've still got 3 red. So that'll be 3 out of 12. And if the first one is blue and the second one is red, the third one, well, there'll still be 6 yellows. So that's 6 out of 11. So that's the probability of one way that you could have 3 tokens that are all different colours. I've only got a limited number of other options, haven't I? For example, if the first one is blue and they've all 3 got to be different colours, then I can only have yellow, red. The first one might not be blue, the first one might be red, and the first one might be yellow. There's only a limited number of options that make this true. So although I've got 27 different branches, if I did draw my tree diagram, I haven't got to worry about many of them. And there's another good thing about that. You'll notice if you do the probability of blue, red, yellow, which we've done here, and compare it with the probability of blue, yellow, red, you'll notice something. And then if you work out the probability of red, yellow, blue, you'll notice something again. So the question 6 is one of the questions that I'd like you to have a go at, and I'd like you to have a go at it without drawing a tree diagram. So what I'd like you to have a go at for me in the textbook, this is the stats textbook on page 79, exercise 5D. Question 1 is a really easy, basic GCSE tree diagram. The events are independent, so the probabilities on the second branches are the same as the probabilities on the first branches. Question 4, that's a conditional probability one, a bit like the one I did about Charlie. And then question 6, that's the one I've sort of started, and I'm hoping you'll be able to get some way with that with no tree diagram. I'd like you to submit your answers to 4 and 6 to me by email, showing me you're working. Obviously you can all find the answers, but I'd be keen to see you working. With question 6, even if you can only get part A and part B done, I'd like to see that, okay? Part C is a bit fiddly. I'm hoping that I gave you a bit of a start to it, but I would like to see however far you get with those 2. So 3 questions, page 79 and 80, it's the same exercise, and the last 2, I'd be grateful if you could submit to me by email. Take care.